we're going to talk now about conduction in very simple geometry. So we're mostly going to talk about one-dimensional problems where we only have to worry about one coordinate direction. So we're going to start with the heat equation. And we're going to make some assumptions. We're going to assume that we have a steady state system. So we're going to simplify the equation by eliminating that time derivative. We're also going to assume that we have no heat generation. And as I said earlier, we're going to assume one-dimensional behavior. So when we do that, we can make this assumption. This is our version of the heat equation that we're going to use for these very simple one-dimensional problems. Now, we have to solve this equation by integrating twice. So when we integrate twice, we end up with two constants of integration. And this is the result. So the temperature here is equal to some ratio between a constant and thermal conductivity times the x position plus another constant, which means that the temperature distribution here is linear. This is what we get for what we call a plane wall. It's basically infinite in the y and z directions, but it has a thickness in the x direction. So now we have to look at our boundary conditions. If we have a Newman or Dirichlet or mixed boundary, we can actually solve for C2. So for instance, if the temperature at x equals 0 is some value, then that value is equal to C2. If we have a heat flux, we go back and we look at the derivative of temperature, which is C1 over x, to get the value of C1. So if we have two Dirichlet or mixed boundary conditions, then we have to write an equation for each boundary and solve them simultaneously. So we have to use those boundary conditions to solve for these two constants. In general, whichever boundary condition you have, if you know the surface temperature at 1 and the surface temperature at 2, we can look at the heat flux, which is negative k dt dx, and that would then be k over L times the temperature difference, where L is the thickness of the wall. And then the total heat rate would then be just the heat flux multiplied by the area. So we can actually use this idea. This is a simple case. There's just a single substance with two temperatures, one on either side. But we can actually use this idea to solve more complex systems. We're going to look at this idea of thermal resistances. In heat transfer, we have the heat rate is equal to Ka over L times delta T. For electrical circuits, we have Ohm's law, which states that the voltage difference is equal to current times resistance. So if we use this analogy that temperature is analogous to voltage and heat rate is analogous to current, then we can see that this term right here can be considered as analogous to 1 over the resistance. So by comparison, looking at the voltage being equivalent to temperature and so on, we get that this resistance is analogous to length over Ka. Now, this isn't necessary for simple problems like this simple plane wall, but it's easier to introduce here. But if we have composite or multi-mode heat transfer problems, it makes it much easier. So if we have multiple walls, if we have convection, if we have what we call contact resistances, which we'll talk about a little bit later, we can actually add up all of these resistances because the heat rate is going to be equal, it's going to be the same here, here, and here. These are resistor symbols. So if those heat rates are all equal, we can write them this way, and then we can look at this temperature and this temperature, and we can relate all of these resistances to that temperature. And when we do that, we get this equation. The total heat rate is equal to the overall temperature difference divided by the sum of all of the resistances. Now, once we have this equation, there are going to be two main types of problems. The first one is if we know the temperature difference and the geometry we're looking at, what is the heat rate? The other type of problem is if we know the heat rate we need and the geometry, what is the temperature difference? And you can see this in nuclear engineering. For instance, in nuclear engineering, the fission rate produces some amount of energy, a given heat rate. And then we have to solve the problem to figure out the fuel temperature and make sure that the fuel is not going to melt under those conditions. So the simplest way to start talking about this idea of thermal resistance is the composite wall. A composite wall is just a wall that's composed of layers of different materials. And each wall, each region, is going to have its own resistance. So we just add up those resistances, and the heat rate is the temperature difference overall divided by those resistances. We can also have composite cylinders or spheres. So these can involve some series or parallel resistances, maybe even contact resistances, where two objects meet. We can have these tiny surface imperfections that increase the thermal resistance of the surface and give us this contact resistance. Typically, we take the contact resistance and express it as some kind of gap conductance, but you'll also see the gap resistance characterized on its own. So then we have to deal with conduction through each layer, and then convection on either surface depending on the boundary conditions for the problem. Now, the contact resistance is going to depend on the joint pressure, which is the force on the joint per unit area. Higher joint pressure basically pushes the materials together, makes them more strongly in contact, and decreases the contact resistance. You can also actually select a fluid to put in between the objects with a high thermal conductivity, or a soft metal or a thermal grease. This is very similar to what you do with a CPU heatsink. You put some thermal grease on the CPU before you put the heatsink on to help improve that behavior. And then for if we solve the heat equation for cylindrical or spherical geometry, we find that these are the expressions for the conduction resistance in a cylinder or a sphere for each layer that we're looking at. So we can also talk about series and parallel resistances. If you have a set of resistances in series, which means they occur one after the other, all we have to do is add up all the resistances to get the total resistance. However, if we have a parallel resistance, like we have here in this problem, the total resistance is actually lower than either individual resistance because the current through each resistance is a little bit lower than the total current. So here we actually have a reciprocal relationship. For instance, in this case, we have a convection and a radiation heat transfer occurring from the same surface at the same time. So in this case, we write this parallel resistance. We have heat rate. So here the resistance is 1 over HA. And for H, we also have an HRAD here, which gives us the radiation heat transfer. And in this case, we have to use this inverse relationship. 1 over the total resistance is equal to the sum of 1 over all, or each 1 over resistance. So we have to be careful about which one we're using. Convection and radiation on a surface is a very common parallel resistance for thermal circuits. And we can also have series parallel resistances. For instance, in this case, we have a conduction from one surface to another surface, and then we have convection and radiation from the surface. So in this case, we're going to convert this to a surface resistance. So 1 over our surface is going to be 1 over the sum of 1 over our convection and 1 over our radiation. And then the total resistance is going to be the conduction resistance plus the surface resistance. So that's how we can use this idea of thermal circuits to simplify heat transfer problems, at least heat transfer problems that are steady and one-dimensional. So here's a quick summary of all of the thermal resistances that we may use. And you'll note that we have the total heat rate right here. Then we have the plane wall, the cylinder, the hollow sphere, and we have convection, radiation, and contact resistances. We can also look at the linear heat rate, which is the heat rate per unit length of an object. We can do this for a wall, we can do this for a cylinder, what have you. So for a plane wall or a cylinder, we have R prime to go with Q prime instead of R to go with Q. And this is a little bit different because now we have some instead of area, we have width, and we've eliminated the length from the cylinder. And then we have all these R prime values for convection, radiation, and contact resistance. And here, instead of area, we're using P for perimeter. And we can also define the heat flux, or Q double prime, which is associated with our R double prime. And here we've eliminated area completely from the plane wall. and we can look at the convection radiation and contact resistance here.